In this video, we're going to talk about the formula for continuously compounded interest. Now, I want to remind you what continuously compounded interest means. And I think the best way to see this is go back to our original problem here where we talked about putting $1,000 in a bank account that gets 8% interest. How much money do you have? It depends, and it depends on how often the interest is compounded. Notice if you compound twice per year, you end up with $1,081.60. 4 times per year, you end up with a little bit more than that. If you compounded 12 times per year, or monthly, that would be, you'd have even a little bit more than this. If you compounded 365 times per year, that'd be daily, you'd have even more. In fact, the more times you compound, the more money you're going to have in the bank at the end of the year. But there's sort of a limit to how good it gets. And the best that you can do is what's called continuously compounded interest. And we found for this example that the best that you could do, the continuously compounded amount, is $1,083.29. So even if you compounded 1,000,000 times a year or 1,000,000,000 times a year, 1,000,000,000,000 times a year, you're just going to keep getting closer and closer to this amount. In fact, if you compounded 1,000,000 times per year, you'd probably only be a fraction of a penny less than this amount. So compounding 1,000,000 times a year or continuously compounded, essentially you're going to end up with the same amount at the end of the year. Even though technically continuously compounded you have a tiny bit more, fraction of a penny more. Oh, and I never answered this question here. It says suppose you deposit $1,000 in an account that gets 8% annual interest, how much money will be in the account at the end of the year? I said it depends, but actually how do banks calculate interest? Well, most banks either calculate interest compounded daily or compounded continuously. Okay, most banks choose one or the other of those. In fact, ultimately, there's not really that much difference. Maybe, unless you had millions of dollars and you had a fairly high interest rate, you're not going to be off by more than just a dollar or two even if you had large amounts of money. Okay, so that's how that actually. So actually, you wouldn't end up with $1,080 in the bank. You'd end up with probably about $1,083 in the bank. Okay, so let's go back to our formula here. What is the formula for continuously compounded interest? It says the compound amount A. Okay, that's the amount in the future for a deposit of P dollars at an interest rate R per year, compounded continuously. Okay, for T years, is given by this formula. Now remember, we're not using N here for number of compound periods because it's almost like our number of compound periods is infinite. Okay, and we're also not using that I, right, interest rate per period, because we'd be dividing our interest rate by infinity. So we're actually back to using R and T for this formula. Okay, so let's do an example. It says the example says, suppose $12,000 is invested at 4.7% interest, compounded continuously. How much money is in the account after 10 years? Okay, so notice that the P, the principal, the initial amount of money is $12,000. The R is 0.047. Okay, that's 4.7% would be 0.047. And the T, what is the T going to be? Well, the T is 10 years. Okay, the A is the thing that we're looking for. So let's plug things in here. A equals P times E to the RT, where the P is 12,000. The E, remember, is that 2.718, whatever, and then 0.047 times 10. Okay, so if we plug this into our calculator, we would get 12,000 times E to the 0.047 times 10, and press enter. We get, let's see, what was that amount? $19,199.93. Okay, $19,199.93. Okay, and again, always ask yourself, does that seem reasonable? If you put $12,000 in a bank account at 4.7% interest compounded continuously after 10 years, yeah, $19,000, that sounds reasonable. Your money would definitely grow over that 10 years. Okay, let's do another problem. And this one, we'll calculate interest a couple different ways. So let's suppose $5,000 is deposited in an account that gets 6% interest. Find how much money is in the account after 3 years if the interest is simple interest. Okay, now simple interest, remember the formula, A is equal to P times 1 plus RT. Okay, the principal is 5,000. The R is 0.06. and the T is 3 years. Now remember, usually we just do simple interest on things that are a year or less. This is 3 years, but let's still calculate it anyway and see what we get. Okay, well I plugged it in a calculator and I got $5,900. So in other words, $5,900. Essentially, I think you're getting $300 each year. Okay, you're getting an additional $300 each year. That's just simple interest. Okay, now here's part B. This almost looks the same. It says how much money would be in the account if you get compound interest, so still 6%, but where you're just compounding once per year. Well, I thought simple interest was the same thing as compounding once per year. Well, it would be the same thing if we were just looking at a 1-year time span. Okay, but we're looking at a 3-year time span, simple interest, and compound interest where you just compound once per year. It's going to be different. In fact, let's look at the formula that we'd use. A is equal to P times 1 plus I to the T. I'm sorry, 1 plus I to the N. Okay, now what is the P? Well, the P, again, is 5,000. Oops, 5,000. The I would be the 6% divided by how much? Well, 0.06 divided by, well, we're just compounding once per year, so it'd just be divided by 1. So it'd still just be 0.06. So in this case, the I is equal to the R because we're only compounding once per year. And the N is the number of compound periods. Well, we're compounding just once per year for 3 years, so the N is 3. So if you're just compounding once per year, then yeah, the N will equal the T, and the I will equal the R. So in this problem, what we end up with is 5,000 times 1.06 to the third power. And when I calculate this on my calculator, I got $5,955.08. Okay, so notice you got more by compounding once per year than for 3 years than you did getting simple interest. Okay, again, compounding once per year is only the same as simple interest if we're just talking about a 1-year time span, but a longer time span you'll get more with compound interest. Okay, let's do part C and D here. Suppose you get compound interest where you're compounding semi-annually. Now let's remember our P is still 5,000. Okay, now our formula again is A is equal to P times 1 plus I to the N. Our I is now 0.06 over 2. Okay, we're getting 6% interest, but we're compounding semi-annually. Okay, so that would be 0.03. And what is the N? Well, the N is going to be 3 times 2. It will be 6. Now, why 3 times 2? Well, it's taking 3 years, okay, and we're compounding twice per year, so the number of compound periods is 6. So if we plug this in, we get 5,000 times 1.03, right, 1 plus 0.03 to the 6th power. And actually, do you expect to have more money than if you just compounded once per year? Yeah, if we're compounding twice per year, I would expect us to have more money. So I expect to have more than $5,955.08. In fact, I got $5,970.26. So yeah, that is more. The other was $5,955. This is $5,970. So by compounding twice per year instead of just once a year, you gained an additional $15 there. Okay, now let's suppose you compound 12 times per year, and then we'll talk about continuously compounded interest. So 12 times per year, we're going to have the same formula, A equals P times 1 plus I to the N. The P is still 5,000. The I is 0.06 divided by 12, which if you type that out, it's I think 0.005, but 0.06 divided by 12, and the N is going to be, well, let's see, 12 times 3, which is 36, right? It's compounding 12 times per year, compounding every month for 3 years. Okay, that was the initial problem, said 3 years. So plug this in, we get 5,000 times 1.005 to the 36th power. And I got $5,983.40, rounding to the nearest penny. Okay, and notice that's more than if we had just compounded twice per year, right? I guess an additional $13 we gained by compounding 12 times a year as opposed to twice per year. Now what about continuously compounded interest? That's the best that we can do. Remember the formula is A is equal to P times E to the RT. Now the P, again, is 5,000. The R is just 0.06, right? We don't have to divide it by anything now. Remember, it's not I here, it's R. And the T is just the number of years. Okay, and the number of years is 3. So let's take our 5,000, multiply it by e to the 0.06 times 3, and I got $5,986.09. Okay, rounding to the nearest penny. So notice, continuously compounded interest, you got even more than if you just compounded 12 times per year. Okay, if you had compounded 365 times per year, it'd be somewhere in between these two numbers, right? You're compounding more than 12 times per year, but you're not doing it continuously, so you'd have a little bit less than this. Okay, so continuously compounded interest, notice that of all these amounts here, this amount, and these amounts up here, which one was the most and which one was the least? Well, the least was simple interest. Okay, the most was when we compounded continuously. Okay, one more thing I want to point out is some terminology. Compounding annually, that means 1 period per year. Compounding once per year. Semi-annually is 2 periods per year. Quarterly would be 4 periods per year. Okay, monthly, you can figure that out. 12 times per year. Daily would be 365 times per year, although some ways of calculating daily would just be 360 times per year. Okay, there I wrote it in. Daily would be 365 times per year, or actually sometimes it could be, for leap year, maybe they could use 366 days, or maybe sometimes they just use 360 to make it basically kind of like you have 12 months, they have 30 days each. But anyways, if it's not stated otherwise, we'll use 365 for compounding daily.